Hello, everyone. My name is Philip, and today we will be covering the awesome, cool things that Chapter 2, Limits and Continuity, will go over. Thankfully, we have a lot of exercises and as well as the same aforementioned examples that will take us, hold our hand, and walk us through every possible type of question that the AP exam may cover. Now, what are limits? Well, if we take it literally and read what it says in the yellow box here, it means where if f of x approaches a single number, capital L, as x approaches a from both sides, then the limit of f of x as x approaches a equals L. What does that mean? Let's say I have this cool little purple curve here. We'll call it the f of x that the example also uses. But hold on, there's a little hole here. There's a dot that goes uncovered, where the graph completely skips over and continues behaving its way. Now, if we were to ask ourselves, okay, despite the graph itself not having a value directly at x, where y value wise is the graph headed to? And we can clearly see that it's headed to this particular value, both on the left side and the right side. But quite frankly, we're talking about how the graph and where the graph is trending to. And if it trends to the same value on both sides, then we can say that it approaches a certain y value, which they called capital L. So, some things to clarify, starting with what does it mean for f of x to have a value? Well, if I say something along the lines of f of 3 is equal to 2, then I am saying that if x is equal to 3, the graph that this function is visualized with will have a y value of 2. But when I say that the limit of f of x as x approaches 3 is equal to 2, that's a bit different. That specifically means that as I'm getting closer and closer to 3 and I look at the surroundings of x equals 3, where is my graph pointing to? And if we look at this example here, it is pointing to a particular hollowed out point, which the graph itself does not pass. But it is pointing to that exact y value. So we have to say that the limit equals 2. Now, that's cool and all, but what is a limit and how do I prove that a limit exists? A limit of a function f of x exists at x equals a if and only if the left-hand limit and the right-hand limit of f of x have the same value of L. The left-hand limit and the right-hand limit. These are some new things that we've probably never heard until now. Thankfully, there's a box on the bottom right. So here you go. Here's a helping hand. But there's another thing that it doesn't really specify, specifically the notation here where there's a negative sign and a positive sign as an exponent of this value a. So what does that mean? Well, when I say limit as of f of x as x approaches a minus insinuates a slightly smaller value than a. And a plus corresponds to a slightly, once again, but larger value than a. And so sometimes variables aren't a great way to understand what it means. So let's use the example of 2. 2 itself is a normal, very perfectly fine number. But what if I added a 2 minus to the top of it? Well, that actually means, again, a value that is slightly smaller than the actual value of 2, which we believe is 1.999999 continuously 99999 onwards. And what about 2 plus? Well, 2 plus does the same thing, but on the other side, aka the right side of the number line, which insinuates 2.000000 onwards 0000 until it reaches 1 on the bottom. Again, ever so slightly small of a value greater than 2, and a value ever so slightly smaller than a value of 2. And so this is where it comes in, when I'm talking about the x value approaching the left side and the right side of, let's say, 2, I'm asking us to separate the case and think about where the graph is headed on the left side of the graph and the right side of the graph. And the example 1 shows you exactly what they mean. We're given f of x is equal to x squared minus 4x plus 3 divided by x minus 3. Find the value of the limit of f of x as x approaches 3. Now, once again, a limit as x approaches a of f of x is equal to L if and only if the limit as x approaches a on the left-hand side, a minus, is equal to the limit of f of x as x approaches a from the right-hand side, a plus. And only if those two values equal an exact value of capital L can I conclude that there is a general limit that is occurring at x equals a. Otherwise, we have to put a stamp of doom that does not exist stamp, okay? Now, where does that leave us? Well, that leaves us with an awesome mathematical process of factoring our numerator and getting that x squared minus 4x plus 3 is actually just x minus 3 times x minus 1. You can check that for yourself, and chapter 1 goes over these exact cases that we spoke about. But now what happens? The x minus 3 factors cancel out. The numerator and the denominator share the same thing. We cancel it out and say, hey, f of x is actually equal to x minus 1, just as long as x is not a permissible value of 3. That means that we have a graph that behaves like y equals x minus 1 as long as it has a hole at x equals 3. And so this graph that they've gratefully drawn for us shows exactly the formula that we've concluded with. So how do I explain what the limit is at x equals 3? Well, I do it by trying some values to plug in. Starting with, let's say, x is equal to 2.9. That is a value that's less than 3 and not exactly equal to 3. So it should have a value in the function f of x is equal to x minus 1. And it does. Y would be equal to 1 minus that, so it's equal to 1.9. Interesting. When x is equal to 2.99, well, again, still not equal to 3, so it should have a value on this x minus 1 line, and it does. It says that when x equals 2.99, y is equal to 1.99. What about when x is equal to 2.999? Well, y is going to follow suit and say, hey, y is equal to 1.99. What about x equals 2.9999? You're never going to guess it. Well, y is equal to 1.9999. Do you see where I'm going with this? Do you see where the graph is headed with this? And so we can carefully and formally conclude that the limit as x approaches 3 from the left-hand side, aka 3 minus, of this cool function f of x is going to lead us to 2. Huh. Cool beans. What about the right side? The right side does something pretty similar, where if I said x is equal to 3.1, again, a value that's greater than 3, not exactly equal to 3, so should have a value in the function, and f of x says yes, y is equal to 2.1. What about when x is equal to 3.01? Well, f of x says, oh yes, y is equal to 2.01. X is equal to 3.001. Well, y is going to be right there with you at 2.001. And you can probably see where the story is going. And you see that when x is equal to 3.00001, y should obviously still be equal to 2.0000001, and so forth. In other words, where is the right side of x equals 3 headed towards? Well, the limit as x approaches 3, the right-hand side, 3 plus, of f of x, approaches 2 as well. Hold on. So the left-hand limit, as we agreed what this was equal to, and the right-hand limit, as we also agreed what this was equal to, both equal 2. And this table below tells us and does exactly what I'm showing you here, which is that as I'm getting closer and closer to 3 from both sides, the limit of f of x as x approaches 3 minus is equal to the limit of f of x as x approaches 3 plus, and they're both equal to 2, and therefore I could be a confident man and say, hey, limit of f of x as x approaches 3 is just equal to 2. And so the y approaches 2 from both the left and the right side. And so therefore we can safely conclude that the limit of f of x at x equals 3 is equal to 2. However, do keep in mind that the actual function itself does not have a value at x equals 3. The function is not defined at x equals 3. And so if I plugged it in, f of 3 does not exist. But the limit as x approaches 3 of f of x does exist, and it's 2. And so what we're trying to teach you is that we can explain the behavior of the graph surrounding a point even if the point itself does not exist. Let's try a couple more examples, see if you get the gist of it. Starting with the first one here, example 2, given f of x is a piecewise function. Bit of a mess here. As long as it's equal to 2x minus 2 over x squared minus 1 when x is not equal to 1, and it's equal to 3 when x is equal to 1, find the value of the limit of f of x as x approaches 1. Now, before I go any further, my awesome math loving brain should say that 2x minus 2 over x squared minus 1 can be rewritten to be 2 times x minus 1 over, well, the difference of squares in the denominator, x plus 1 times x minus 1. And so it factors out once more, much like the previous example. And I say, hey, f of x is equal to 2 over x plus 1 as long as x cannot equal 1, like they said, thankfully, about this part of the piecewise function. Phew, a quick overlap. And so I can safely say there is a vertical asymptote in the function when x is not equal to 1. Specifically, a vertical asymptote of x equals -1 and a horizontal asymptote of y equals 0. Why is this important? How am I drawing the graph? Well, the graph, at least the first part of it, is a cool graph. But as long as x is equal to 1, it's going to obey the second part of that piecewise function where x is equal to 1, then y is equal to 3. Now in this case, at x equals 1, the function f of x does have a value. It is equal to 3. But how do we explain the behavior of the graph around x equals 1? And that's what we're going to do again, where starting with the left-hand side, let's say when x is equal to 0.9, what does the graph look like? Well, using the function that f of x is equal to 2 over x plus 1, as long as x is not equal to 1, I say, hey, y is equal to 2 over 0.9 plus 1, and so that approximates itself to 1.0526. What about x equals 0.99? Well, good ma'am or sir, I say that y is equal to approximately 1.00503. Okay, what about x equals 0.999? Well, y is going to be equal to 1.00050. Okay, what about x equals 0.9999? Surely the graph follows a trend. And it does. It says that y is equal to 1.00005. And so we can conclude that the limit of f of x as x approaches 1 from the left-hand side actually approaches 1. Cool beans. But what about the right-hand limit? Well, if you follow the table like everything else so far, you'll get that they agree that the limit of f of x as x approaches 1 from the right-hand side this time, 1 plus, is also equal to 1. Wait a second. And when I look at the graph, I have to agree. The left-hand side does go down to a y value of 1 as I get closer and closer to the x value of 1. The right-hand side does the same thing, where as I get closer and closer to 1 from the right-hand side, its y value is getting up there to 1. And so the left-hand limit and the right-hand limit do equal each other, and they do equal 1. And so I have to conclude that the limit of f of x as x approaches 1 is equal to 1. Huh. Funny. Even though f of 1 itself, when plugged in, turns out to be 3. The behavior of the graph is telling me that the graph is trending towards y equals 1. And the yellow box is saying the same thing. The y value approaches 1 from both the left and right hand sides, and therefore the limit of f of x as x approaches 1 is 1. But the exact value of x equals 1 in the function f is actually equal to 3 up here. Ta-da! And so this brings us to example 3, where another piecewise function f of x is equal to 2 minus x as long as x is less than or equal to 2, or x if x is greater than 2. And they want us to find the value of the limit of f of x as x approaches 2. Now, they've done a beautiful job graphing it for us, and you'll probably feel very grateful that a lot of the examples come with a graphical representation. And in this case, I'll recognize something that I could also recognize by trying the neighboring values of x, starting with x equals 1.9, a value less than 2, and so it obeys the first half of the piecewise function. It would be that y is equal to 2 minus 1.9, which is 0.1. Okay, what about when x equals 1.99? We're getting closer to 2, but still on the left side, and y is equal to 0.01. Okay, what about when x equals 1.999? Well, best believe it, y is equal to 0.001. What about when x equals 1.9999? Well, hey buddy, y is equal to 0.0001. And so we can conclude that the left-hand limit, at the very least, so the limit as x approaches 2 minus, is equal to 0. But what about the right-hand side? So by the right-hand side, I mean values, for example, x equals 2.1, a value greater than 2. So it obeys the second half of the piecewise function, where if x equals 2.1, y is equal to 2.1. Okay, interesting. Not close to 0 at all. Maybe it changes? Well, when x equals 2.01, y is equal to 2.01. Oh, interesting. What about when x equals 2.001? Y is 2.001. X is 2.0001. Well, that's still greater than 2 technically, and therefore y is equal to 2.0001. And we know where this story is going. And so we say the limit of f of x as x approaches 2 from the right-hand side is equal to 2 as well. Hey, hold on. So the left-hand limit goes to 0, and that's what the graph is telling me, yeah? And the right side of 2 is going closer to 2, so they're not equal to each other. And so we say that the left-hand limit does not equal the right-hand limit, and therefore a general limit to describe the general behavior of x equals 2 does not exist. And so following the conclusion of the yellow box, we say that the y value approaches 0 from the left side, but approaches 2 from the right side. Therefore, the limit of f of x does not exist at x equals 2. When I plug in x equals 2 directly into the function f, I say, oh boy, f of 2 is equal to 0. So, the three cases that we've covered is one where the direct value of x does not exist, but we can describe the behavior around that x value. The second example talks about how there is an x value, might not exactly be equal to the limit, but both exist. And the third example is one where the left-hand behavior and the right-hand behavior of a graph near a point do not coincide, even though a direct value, x equals 2, does have a value. Now, knowing what we know from examples 1 through 3, let's see if we can use it to our advantage in example 4, where they give us a graph that looks slightly unusual, but we have to describe certain parts of it using the limit notation. Starting with 1a, the limit of f of x as x approaches -2 from the left-hand side. What is happening to the function as I'm approaching 2 from the left-hand side? Well, the y value is approaching -2. What about B, limit of f of x as x approaches -2 from the right-hand side. Well, the right-hand side tells me a different story, that it's approaching a y value of -1. And so now tell me, does the left-hand limit and the right-hand limit at x equals -2 approach the same y value? No. And so we say it does not exist. A general limit of f of x as x approaches -2 does not exist. But at f of -2, directly, it does equal -1. Just plug and play, and you'll recognize that the colored in circle represents the actual part where the graph overlaps. What about when x approaches 0 from the left-hand side? Oh, you betcha it's equal to 1. What about when the limit of f of x as x approaches 0 plus? Okay, from the right-hand side, oh, it's also equal to 1. And so, by golly, the left-hand limit and the right-hand limit as x approaches 0 is the same, and therefore I say that the limit of f of x as x approaches 0 is also equal to 1. But is there a y value if I plugged in x equals 0 into the function? No. Therefore, f of 0 does not exist. Now, what about number 3a? X approaches 2 from the left-hand side. 2 would be here, and oh, we're going way off the graph, and it seems like it's never coming down anytime soon. And we say that the limit of f of x as x approaches 2 minus is positive infinity. What about as it's approaching 2 from the right-hand side? Whoa, oh my god, it's doing the same thing. It's going down there and never coming up, especially because of the asymptotic behavior at x equals 2. Therefore, we say that the limit of f of x as x approaches 2 plus is -infinity. Now tell me, do they equal the same thing? No, and therefore the limit of f of x as x approaches 2 does not exist. And more specifically, is there an exact value at f equals 2? No. So still does not exist. Last but not least, and let's use a cool little purple color for this one. What about when limit of f of x as x approaches 4 minus? Well, the left side of 4 tells me that it is approaching a y value of 2. What about the limit of f of x as x approaches 4 plus? Well, the right-hand side of 4, well, it's telling me it's also approaching a y value of 2. And so if the left-hand limit and the right-hand limit can agree on a single y value, you say that the general limit, the limit of f of x as x approaches 2, is also equal to 2. But hold on there. Is f of 4 also equal to 2? Rather, when I look at the graph and I see what's given to me, I see that at x equals 4, f of 4 actually has a y value of 1. So, do we understand what we've done so far? Do you? Then let's try a couple examples together. Starting with exercise 1, use the graph of f to evaluate the following. Very similar to the example question we just solved, wasn't it? So, limit as x approaches -2 from the left-hand side. Boy, it looks like it's approaching a y value of -1. But what about as it's approaching -2 from the right-hand side? Well, it looks like it's approaching a y value of 1. And those aren't the same. The general limit of f of x as x approaches -2, does not exist. And moreover, there is not an exact value of f at x equals -2. Now, what about as x approaches 0 from the left-hand side? Well, we see that it's going to infinity and beyond. So we're going to write down positive infinity. What about when limit of f of x as x approaches 0 plus, aka the right-hand side? The right-hand side of x equals 0. Well, that looks like it's approaching a y value of 2. Now, is positive infinity equal to 2? I don't think so. You say, oh, it does not exist. And therefore, f of 0 also does not exist. Oh, psych. It's actually going to be equal to -2 because if I plug in f of 0, I will get a point that's hanging all the way down there. What about when limit as x approaches 3 from the left-hand side? Whew, it goes to -infinity. What about when the limit of f of x as x approaches 3 plus? Well, oh, it's also going down to -infinity. And so, now survey says that because the left-hand limit and the right-hand limit both look like they're approaching -infinity, I can confidently say that the general limit of f of x as x approaches 3 is also equal to -infinity. But be warned, certain schools like to emphasize the fact that a limit can only exist if they're both approaching an exact non-infinite value, aka they want it to equal a 2, a 3, a -5, a -20, a 15, a 17. They want it to be a number on both the left-hand limit and the right-hand limit. And if your school uses that kind of philosophy, try to remember that, because that's how you're going to get points. But the common nomenclature is that the limit of f of x as x approaches 3 minus being negative infinity, and the right-hand limit 3 plus also being negative infinity, implies that the limit of f of x as x approaches 3 is also equal to negative infinity. Heed my warning. But f of 3, well, I look at this bad boy here and I say, well, its y value is equal to 1. The final row there, for a, limit of f of x as x approaches 4 minus, so left-hand side, everyone, and we see that it's getting closer to 0. What about when limit of f of x as x approaches 4 from the right-hand side? We see that, oh, it's also approaching 0. And so the limit does exist, and it does equal 0. And on top of that, f of 4 also has a value at 0. Now, we will end the video here, but in the next one, we're going to be talking about cool properties about limits, awesome arithmetic tricks we can do with them, and also certain things that we call indeterminate forms. I'll see you there.